Hello everyone. In this video, I am discussing with you a numerical approach to solve the numericals based on transformer losses and efficiency. So, I'm not going in much detail of the theory related with losses and efficiency. These all points I will discuss with you through this numerical. So, first let us start with the numerical. Slowly, I will tell you the concept related with this numerical, and at the end of this numerical you will be able to understand all the concepts related with losses and efficiency. So here is the numerical. A 5 kVA 1000/230 volt 50 Hz single phase transformer has 500-watt constant loss. Copper losses are measured 300 watt when 3 ampere current is flowing in high voltage winding of transformer. For this given transformer, evaluate the following. Number 1, core loss. Number 2, copper loss. Number 3, copper loss in transformer at full load current. Number 4, efficiency of transformer when full load of 0.9 lagging power factor is connected. Number 5, efficiency of transformer when half load of 0.9 lagging power factor is connected. Number 6, load on transformer at the time of maximum efficiency. And number 7, maximum efficiency of transformer at unity power factor. So this is the numerical which is related with the topic of transformer losses and efficiency. You see, any numerical has two parts. First, the data which is given to you. Number 2, the values which you have to evaluate from this numerical. For evaluating some parameters, you require some mathematical expressions. Before starting your numerical, you should always try the following step. Number 1, try to write all the given data together. Number 2, then you write the formulae required for solving this numerical, and in last step you try to find all the required parameters one by one. So let us start this numerical by writing the given data over here. You see, the transformer is of 5 kVA. This 5 kVA represent the rating of the transformer. This rating is normally represented by capital Q. So the value of capital Q is 5000 VA. K stands for kilo. Next, 1000/230 volt. This means that the voltage at high voltage side is 1000 volt and low voltage side is 230 volt. The frequency is 50 Hz here. The constant loss of the transformer is 500 watt. In transformer, core loss, or another name is iron loss, are always the constant value. So whenever we have the value given like constant loss, iron loss or core loss, these all three things are similar, and the parameter is represented by pi is used for defining these three value which is equal. Name is different, but these all three things, constant loss, core loss or iron loss, are the same thing. So you see here I'm writing core loss equals to core loss, constant loss equals to core loss equals to pi, iron loss equals to 500 watt. Next is copper losses are measured 300 watt when 3 ampere current is flowing in high voltage winding. In high voltage winding means 1000 volt side, the current flowing in the transformer is 3 ampere. At this current, the copper losses are 300 watt. You see, the copper losses depend on the value of current. Here, the value is 3 ampere. At 3 ampere, the losses are 300 watt. When we are changing the value of current, at the same time, the copper losses will also vary. And therefore, we can say that this copper loss is a variable loss in the transformer, right? So after getting the information of all given data, the second point is we will try to write all the formulae together which we will use in this problem. So you see, first formula is PC equals to x square PCFL. As I told you, that copper loss depend on the current flowing in the transformer. In other term, we can say the load connected on the transformer, because we know the current flowing in the transformer is proportional to the load connected to the transformer. If more load is on the transformer, more current will flow in the transformer. So we can say in the term of the load that PC is x square PCFL. PCFL is the copper loss at full load. FL stands for full load. The value of this x can be evaluated by three methods. Normally in the problem, x can be given by any one method. Suppose in numerical it is given that zero point 0.5 load is connected. This means direct fraction of the load is given, so you will use x equals to 0.5. Second method in problem, they can say that 3 kVA load is connected at 5 kVA transformer. So the transformer rating is 5 kVA, but the connected load is only 3 kVA. So the value of x is applied load means 3 divided by transformer maximum possible load, that is rating of transformer, which is 5. So 3 upon 5, this will give you 0.4. Third method, load percentage is given. In numerical, they can say that 50% load is connected or 60% load is connected. So if 60% load is connected, this means x is 60 upon 100 is 0.6. So in this way, we can find the value of x. Next is the formula for the efficiency. You see here, efficiency formula is given by this expression xq cos phi divided by xq cos phi plus pi plus x square PCFL. Where x, I have told you here that how can we find the value of x. Q, as you know that Q is here, we have seen that Q is the rating of the transformer in VA. Next is you see cos phi. Cos phi is the power factor of the load. This value will be given in the problem. Pi, same iron loss, core loss or constant loss. And last, PCFL, the same as here, copper loss at full load. Next, you see efficiency of the transformer depend on this value of x. If we are changing the load on the transformer, the efficiency will change. But there will be a certain point at which we will get the maximum efficiency from this transformer. So first we have to calculate what would be the value of x. As I told you that the value of the x may be like we are connecting 20% load, 30% load, 50%, 60%, 70% and so on. So we can get the value of efficiency at any load, but at certain load the value of the efficiency will be maximum, and this can be calculated by this formula pi equals to x square PCFL. This value of x will be the value at which the efficiency of the transformer will be maximum, and the value will be given by this formula xq cos phi upon xq cos phi plus, you see these two parameters are equal now from this expression. So x square PCFL I am replacing with pi, so I am getting pi here. So now we have all the formula together. By using the information of the given data and the information which we have from the theory, that is the mathematical expressions, now we can solve this numerical and can give the answer for the required statement, asked statement. You see here, the first point is the core losses in transformer. So as I told you that the given constant losses are the core loss. So Pi is 500 watt. Second is copper loss in transformer. So at 3 ampere current which is flowing in the transformer, the copper losses are 300 watt. So here you see 3 ampere current, the copper losses are 300 watt. So copper loss in transformer simply 300 watt we can write here. The third point is copper loss in transformer at full load current. Now they are asking the copper loss at full load current. So first we will check what is the value of full load current. You know that Q is equals to VI. You see from this, that is, this Q is, the unit is VA, means volt and current. So Q equals to VI. For this, you see 3 ampere current is at high voltage side. So high voltage, what is the value of voltage here? 1000. We have written here also. This means if I will divide Q with V, what I will get? I. So I will be Q upon V. And since I am putting the highest value of Q and highest value of V, I will get the highest value of the I. In other words, I can say that since I am putting the full load value of transformer, I will get the full load current for the transformer. And by substituting here Q upon V, which is 5000 upon 1000, I will get the value 5 ampere. This means in transformer, the value of full load current is 5 ampere. But the losses which is given to me, 300 watt, these losses are at 3 ampere. So I have to calculate the copper loss at 5 ampere for this full load current value of copper loss. So how can I calculate? You know this formula that P is proportional to I square. Simple ohmic loss. P equals to I square R. From this expression, you see I am using the symbol that copper loss at 3 ampere divided by copper loss at 5 ampere is the current at 3 ampere and current at 5 ampere. Now substitute 3 ampere upon this equals to 3 square upon 5 square. This copper loss at 5 ampere is simply the copper loss at full load, because we are evaluating at 5 ampere and 5 ampere is a full load current. So we can write this PC 5 ampere as PCFL also. So the value of PCFL, when we will solve this expression, we will get 833.33 watt. So this is the answer for the third point. Now the fourth point is efficiency of transformer when full load of zero point 0.9 lagging power factor is connected. So you see from this statement, full load means the value of X is 1, right? And power factor is given to you 0.9. So you know the value of X, you know the value of cos phi, and you have to find the value of efficiency. Efficiency is given by this formula. You will put all the values and you will get the relation like this. Next, you see the efficiency of transformer when half load is connected. So everything will remain same except X. So you can substitute X equals 2.5 and you will get on solving efficiency like this. Load on transformer, you can find at this load the efficiency of the transformer will be maximum, and when you will use submit the maximum efficiency of transformer at unity power factor given in the numerical. So when you will put the value of X, the value of cos phi is 1, other values are same, you will get the maximum efficiency 79.48%. So this is all about this numerical.